Hey everyone, welcome back to my channel. Today we're going to be working on problem number 653. It's called 2 sum 4 or 5. I believe this is 4. Input is a BST. So this is a problem that I have never worked on in the past. It's pretty much similar to a problem that's called 2 sum. It's a very famous problem, but the input is an array. But this time we're given a binary search tree. So given the root of a binary search tree and a target number k, return true if there exist two elements in the BST such that their sum is equal to the given target. So for example, we have a BST 5, 3, 2, and then 4, and then the output is 2 because k, which is target, is equal to 9. So 6 plus 3 is 9. And here we have this, and k is 28. Nothing in this equals 28. So there are no two numbers that equal to 28. We can go through this one by one, checking each other one, but that's going to be take a long time. So we'll just trust the website. The number of nodes in the tree range is in the range 1 to the 10 to the power of 4. Negative 10 to the power of 4 is less than or equal to node dot val, which is less than or equal to 10 to the power of 4. So these two but just mean that the possible length goes from 1 to 10 to the power of 4, and then the possible values goes from negative 10 to positive 10 to the power of 4. Root is always guaranteed to be a valid binary search tree, and k is also, which is the target, is in that range. So the first step is to actually go over the steps that we would do in a normal interview. So the normal steps are writing the algorithm or designing the algorithm without actually writing it, and then any edge cases, and then the runtime, and then the space-time complexity, which is both of these are represented by big O notations. So let's go over any edge cases before even going over the algorithm, because we want to clarify we fully understand the problem, and we do that by going over the edge cases after reading the problem. So the edge cases in here are pretty much defined, because we know that the node will never be null or empty, and there are negative numbers, and the fact that it's a binary search tree. It says the root is always guaranteed to be valid, and k, okay. And if there will be a time where obviously there is no sum, so as long as there is a sum, we are returning true. So very similar to the 2 sum. So let's go over the algorithm. Very similar to the 2 sum approach. What we can do, there are two techniques. One is a brute force, which is for every single node, we check if there exists a node so we traverse the tree every single time and see if there is another node that equals to k. But that is obviously a O of n squared solution, but what we can do is use a hash map or a hash table. And by that, I mean what we want to do is we want to have the summation of 9, right? So 3 plus 6 is 9. So as we traverse the tree, we add 5, and then we add 9 minus 5. So the target is 9, and 5 should give us 4. So anytime we find 5 and 4, like these two, we can return true. Or 3 and 6. In this example, it's a pretty good example because every other node that remains is a summation of 9. That will be O of n. Let me see if we can do it in O of log of n. So let's say we go to 5, 6, 7, 8, 9. So if there exists a node that is less than 5, we can just traverse the left subtree. but then there's not always a guarantee that the 4 is here, right? So in the worst case, you would still have to check the right subtree for the opposite value. So the algorithm will still be of n. And basically all we do is use a hash map with the current val as key and the subtracted value as value. And the subtracted value from the target as the value. Let's put this in here. So for example, let's say we're at 5, we add 5 as the key and then 4 as the value. Then we go to 3, then we check does 3 exist in the value or the key. If it does, that means, so for example, if 3 exists as a value anywhere inside the map, then we know that there exists something else. Then we check for 4, is there a value for 4 inside the map, or is there a key for 4 inside the map already? Then we add that. So first what we'll do is 5 and 4, then we'll go to 3. 9 minus 3 is 6. And then we'll check, alright, is there a hash map that contains 6? So if it does, then we just return true. So for this, we can just write down another DFS where we pass in the root, k, and then map, and then we create a hash map. Integer map equals new hash map. And let's see, let's say we have a DFS. Let's make this a void function now. And here we have tree node root. And then we can just copy this as a parameter. And then this, the target. And k. Then we do if root equals null, then we just return. Otherwise, what we can do is map.put root.val, and then if root.val is greater than k, then we do map.put root.val. So if the root.val is greater than k, so no, sorry, if root is guaranteed to be if root.val is greater than k minus, sorry, if the root.val is greater than so 9 minus 5. Then it would be root dot val minus k. Otherwise, we would do map dot put root dot val and then k minus root dot val. So k minus 5 is 4. Then we want to just check if root if map dot contains key out int such equals 0. So what we do is subtract equals root dot val minus k, and then we just add k and subtract in here, else we do subtract equals k minus root dot val, and then we can just do subtract equals contains key. So if the map contains key k minus 9, 9 minus 5 is 4, subt or map dot contains value subtract, then what we can do is like return true. But so we can just put output equals true and boolean equals false. Then we just do DFS and we pass in root and then k and then map. And then instead of root, we just do root dot left, and we recall this function root dot right k map. So if root dot val is greater than k, we do root dot val minus k, otherwise k minus root dot val. So 9 minus 4, then we add it to the map, root dot val subtract. So it would be 5, and then 3, and then we go here, and then we check, alright, so we add map.put 3, and then 7, sorry, 3, and then 6, and then we come here, and then we come here, then we check, alright, does map contain subtract, so 9 minus 4 is 5, then we return true, and then in the end we just return output. So this checks out. Let's try to test it out. Let's test it on all edge cases. Why is this working? Output was true. If map dot contains key, So I am not sure. Let's try to debug this. So 5 and 9 minus 28 is, I'm sorry, 28 minus 5 is, let's quickly debug this. If 5 contains key, oh, obviously, because we just added, it should be k. Sorry, let's try to run this now. What's wrong with this? Hold on, if map.contains key subtract, so 5 minus 9 minus 5 is 4. We add 5 and 4. 9 minus 3 is 5. 6, sorry. So we add 6 to the value. 4 if contains key subtract. Okay, so this should work. 2, 1, 3. 1. Or map.contains key. So it needs to be so you add the value contains, hold on, and here you have 2, 1, 3. The output is it should be 5 minus 9 minus 5 is 3, 9 minus 5 is 4. If map that contains value, 9 minus 4. Hold on. So 9 minus 4 is 5. We will not always find a contained value in that case. Come here, we add 5 minus 9 minus 5. If root.val is greater than k, subtract equals root.val minus k. So root.val is 5. And then we add the subtract, which is 4. Then we check if map that contains key, subtract, no, come here, the key we add 3 and then 6 and then 2 and then 7 and then 4 and then 5. Then we check 9 minus 4 is 5. If map.contains key of 5, that 9 minus 4 equals 5. 6, 9 minus 6 is 3. So why doesn't this work? You need two sums. 1 minus 2. 2 minus 1 is 1. So 2, if map that contains value, should be contains key. 2. So for this, you would do if root.val is greater than k. No, so 2 minus 1 is 1. So you would add 2 and then 1. If map.contains key, no. Then you do 1 minus 1 is 0. If map.contains key. How is this failing? Yeah, so this should not be the case. How? 2 minus 1 is 2. K minus root.val is 2 minus 1 is 1. And map.put root.val 1 and then 1. If map that contains key what we need is 2 minus 1 is 1. So it's 1 and then 1. If map dot contains key uh 2 minus 1 is 1. If map contains key um and map dot size is greater than 1. So 1 and then 2. If I got true, 6 minus 3 is 6 minus 2 is 5. I'm sorry, 4. Why is this algorithm returning true? 6 minus oh um should work now because we're checking against 3, 6. Sorry, I think it's because we were checking the key against the value 2133. What's wrong with this? What? 2 3 minus 2 3 minus 2 is 3. 3 minus 1 3 minus 2 is 1. 3 minus 1 is 2. If map dot contains key subtract and map dot size is greater than 1, output equals true. If map dot contains 2 minus 3 minus 1 is 2. Why isn't this working? Okay, 1 is 2. 2 is 1. Okay. 3 minus 2 is 1. And then 3 minus 1 is 2. If map dot contains key 3 minus 1 is 2. False. What was the this right here. Not this one. There was an edge case. It was 1 and 2. Okay, let's try with another edge case, 1 and then 2, and see what we get. Okay, now let's try to submit it. Please work. Okay, great. So I apologize for the hiccups. There were several edge cases that I missed. Yeah, typically, I don't know. I feel like I wouldn't have those problems. I had the algorithm down, but order of operations is a thing, and I mistakenly put this right here, and the algorithm was not working efficiently. Please do let me know how I could have improved. Thanks. Bye.